Okay, so as far as a process, like I said, the problem is I. You can't just use MC over I with its, I calculated strictly by the geometry, because it's a non-homogeneous section. So you have to use what's called a transformed section. You transform your composite into what it would be like if it were all made out of the same material. And then you calculate I for that. So what I'm doing is I'm saying, okay, here, and this one's just a little bit more complex, but it kind of makes the point. I've got wood, right, and I've got steel in the center, and I've got aluminum on the outside. So I want to convert that into something that would have equal stiffness, because I is a measure of the stiffness, right? It'll have equal stiffness, but it'll be made entirely out of wood. So I convert the steel here in the middle. If I made the steel entirely out of wood, it would be, I'd have to make it that thick. So I change the thickness because I'm going to take the moment of inertia about that axis. If I change the depth of it as well, then that would be adding another component to stiffness, right? It would be getting stiffer because of the depth. So I don't want to do that. I just want to keep it linear, and I just add the thickness in the direction that's this way along the axis, parallel to the axis, I guess. And my aluminum out here, okay, it's not quite as well. It's almost the same stiffness, 35, but it's much thinner piece in this case. And it becomes this piece out here. So it keeps the same depth, but I just make it thicker. So now this is what the same thing of what that composite would be, but it's made entirely out of wood. It's a ersatz, right? It's a fictitious construct. You're not actually going to make it, obviously, but now you can calculate the moment of inertia for that diagram, and it will give you the correct moment of inertia. This is the transformed section moment of inertia. So this is, and then we can use that in the moment equation. Now the way we find the width of these that we need is with this scale factor called the modular ratio. And it's simply the ratio of the E moduli, right? So I'll take as a base material in this one I'm playing with here, the base I'm taking is the wood, and normally that works out pretty well. If you take the wood's going to be the lowest E modulus, so if you take the E modulus for the wood, that kind of makes a good base, and all the other numbers are going to be. All these are going to be scaled up. They'll all get thicker. And so in this case, what did I have? The base, the wood, my wood was 1 point, if I can read this right, 1.5, all right? 1.5 times 10 to the third. And if I look at the steel here, it was 36. So my modular, oops, I had a calculator here someplace. See if we can do this right. 36 divided by 1.5 equals 24. Okay, then I say 24 times a half, and should have gotten 12. Somehow I got 10. What did I do wrong? Oh, yeah, right. Okay, 30. Sorry. It's 30. I grabbed the wrong number. I was looking at the stress. It's 30. Okay, so 24. Okay, 30 divided by 1.5 should be 20 then, right? Okay. And then 20 times a half is at 10. Okay. And the other one, aluminum, let's see if I can get the right number now. That's 12. So it would be 12 times 1.5. Let's see what that is. 12 times, so it's 12 divided by 1.5 equals 8. Okay, and then I take that 8, that's the scale factor, 8 times 1/4 of an inch, and that looks, yeah, I think that would give me the 2 inches then. So that's how I'm scaling these up, is by this ratio of the E-modulus. Okay. Okay, so, and then you simply calculate the transform section, calculate the moment of inertia. In this case, they all line up, so it's just a matter of adding, summing these. If you had, like that example I had with the column, if I was using something like that for a beam, then I'd have to use the AD squared term to get it'll turn into an I section. We'll do an example like that as well, just to realize the difference. But the normal case is probably more like this one, and it's just a matter of adding the different BD cubed over 12 to get the total. Okay, so let's see what the process is. So if we're going to do the analysis of a Flitched beam here, and I think I did do this one, start by determining the modular ratios, right, of each of these materials. Take usually the one with the lower E, this would be the wood as the base. So that's what we've got here. These are the modular ratio of whichever these materials are. Let's call this one the base, the wood, and maybe the steel is A, and this one is C. So you'd end up with these. This would be for the ratio for the steel, and this would be the aluminum in this case. And the wood is the base material. This is where the wood is. So of course the NC, if you wanted to make to be consistent, you could even, and that way you could use this same equation for all of them. You could have an NB, right, for the wood, but it would be EB over EB, right? It would equal 1. So it has no effect, right? I mean, you'd be scaling the wood. The wood's already the full scale. So, okay. And then once you've done that, you calculate the moment of inertia of the section, and then you calculate the flexural stress with this formula, MC over I, but you've got to do it for each material separately. So you have to do, in this case, the wood, and the ratio for the wood would be 1 here. You could do it for steel and get the stress in the steel, and you'd have to use the proper, that would be the NA, right, is what we were using up here. So you have to use the N, the modular that matches the material that you're trying to get the stress for. Okay, so here we go. This will be this one. And this will be, again, a pass-fail analysis. We've got some sort of crazy beam loading here that we can calculate the moment that we'll need, and that'll plug in here, and then we can calculate the stress and see if we are within these stress limits. So for the wood, this is basically FB, and the others will assume they're FY. Okay, so we get the modular ratios for the wood. If you want to make it, it would be 1.0. For the aluminum, we put the aluminum over the wood. These are the ones we figured, and the steel comes out as 20. So those are the scale factors that we're going to scale the widths by to get the transformed section. So we make the transformed section. They've got these widths like we did. The wood doesn't change. It's the same. And in this example, they have full dimension pieces. I mean, it's a full 2 inches by 12 inches, but okay. And then we calculate the moment of inertia, which is just simply with pt cubed over 12, right? pt cubed, or h cubed over 12. Okay, so we do it for, I did it 2, 4, 6, 8. There's the 8 that are 12 inch deep, and then 10 by 8. 10 by 8 is that center section, and you add them up, and it gives you the moment of inertia. So we got the moment of inertia. Now we can plug that. Well, okay, then we have to know the moment. Since we're just given the beam loading, we can calculate the moment. You can do these lovely shear and moment diagrams. I guess this is a parabola, right? So this must be base times height over 3. I think this is. You might have to look this up, but I think if you take a parabola, that part is 2/3, and this part is 1/3 on a parabola. So that, let's see if that's right. 6 times 12 divided by 3 would be 2 times 12 is 24. Okay, so that looks right. And you get then 24 for that. Or you could just somehow you get that center moment, and that then is going to be the moment that we plug in, and we'll have to do each of these separately, right? The aluminum, the steel, and the wood. So the moment is going to be what we just found. We plug that in. That's constant for all of them. Okay? And the the moment of inertia, is also constant for each one of them. So what changes is this C, of course, because we've got the steel has got a little bit lower. Here we've got the C. This is our center line. Here we've got a C of 6 inches, and here it's only 4 inches, right, for the steel. So we've got, for the aluminum, we're using the 6 inches for C, and we've got to use the scale factor. That goes in here to kind of descale it, right, for the aluminum. And that gives us then the stress in the aluminum, and you can compare that probably to 0.6 times 35, which is, let's see what that would be. This much is still way over. It would be 21. Okay, yeah, so that's 21 is way safe. Okay, then we can look at the steel. That's only got the 4-inch depth, right? That's this depth here, and the scale factor of 20, the modular of 20, and that comes out to be only 14. And that, I think, for steel, FB is 21.6, right? Is that what 36 times 36 times 0.6 equals 21.6? Yeah. Okay. Okay, so that's good. And then the last one, the wood is also at a 6-inch depth, C, and doesn't really have a scale factor. or scale of 1, and that comes out to be 1.09 KSI, and if we say this was probably supposed to be FD, if we take that out of the, assume that came out of the NDS with all its appropriate adjustment factors, then we'd be passing. So that's a procedure. You go through step by step, and now we could do one that's a little more complex just to see how this works with the when you don't have the plates on the sides, because it's much easier to calculate. Here now with the plate top and bottom, you'll see we have to use the parallel axis theorem to calculate the moment of inertia. Okay, so this is going to be another one we want to find now, load capacity. So given this member, if we really want to use this like that in flexure, and I noticed I had this is the stress from the 2015, the changed redwood in the 2018 code, but that was the 2015 version. Okay, and right, and we want to know how much load this can carry. All right, so we've only got one material to worry about, the steel. 29,000 over 1,000 gives us a modular number of 29. Okay, so we're going to scale this, and now remember the flexures looks that way, right? This is the XX, so I can't change the depth. I just have to make it wider. So this is where it's a little different than that other example. You end up with something like this. I'm making it wider by that scale of 29. It was 3.5 times 29. Now it's 101.5 wide. Okay, but now I can't simply sum up the moment of inertia. I have to account for the 80 squared term. Or actually, I was looking at this yesterday. You could, there's the other way to do it by solid and voids. You could look at a solid and then just subtract out these voids, which you could do by, but it's not that much of a difference, one way or the other. So by using the parallel axis theorem, we get for the wood in the center, there is no D term, so it's just BD cubed over 12, right? BD cubed over 12. So we get that for the wood. For the steel, there are two sections. The BD, this part is the BD cubed over 12, right? That's this. There's the D cubed. And then I've got to add the AD squared term. So this is the area and the D squared. And the D squared that's the D. So that must be the 2.8, whatever, 75. From the center down to the neutral axis. Okay, so we get that and sum it up, and that gives us then the transformed section moment of inertia, 468. Okay, now we've got to make sure that we don't overstress either of these two materials. We got the steel and the wood, and we want to make sure that we don't overstress them. And the stress is proportional to strain, so we could look at either one, actually. We could look at the stresses, or we could look at the strain. So here I'm going to say, okay, let's look at this. If I take this as the stress limit for the steel, then this would be the strain limit, right? So here's the the strain is equal to the stress over the E modulus. So for the steel, I take this stress I've got, and I'm just calculating what this strain would be. So this strain is this one. So that would be the limit of how much I could strain the steel before I get into trouble. I'd exceed the allowable. And for the wood, it was 0.725 actually. I abbreviated a little bit. Over 1,000,000. So that gives me a strain for the wood of this amount. So I can't strain the wood beyond that. So I could construct the strain diagram, and if I choose, I can choose one or the other. Right? It's got to follow a linear relationship here. The strains are linear, so I could pick either this value, or I could pick this top value and then calculate the other one. I pick one and calculate the other one. So in this case, I picked the top one, and I set it equal to the limit of the steel. This was there's the limit of the steel, right? So I'm setting that equal to the limit, and then I calculate the other one. Now when I calculate this one, it's either going to be above or below the limit for the wood. If it's above the limit for the wood, that means the wood is controlling, and then I'd have to throw out that calculation and start over again and set the wood to be the limit of the wood, and then calculate the steel, and the steel would come out lower. In this case, it worked out okay because I chose the top one, and when I calculated the wood, it is lower, right? It's lower. This is 683, right? So that's lower than the 725. So in other words, the wood is not strained above its capacity. It's safe. So in that way, I've determined what the strains are, the allowable strains for each material, and then I can simply calculate the stresses in the material. So given that strain, well, that's how I got that strain, was based on the maximum stress. I have that stress. If I wanted to calculate, I mean, I don't really have a reason to, but if I wanted to calculate the rest of the diagram, you could simply take at this strain, find out what the stress is in the steel. So I think I did that somewhere. Yeah, that's this here. Here's the E modulus for the steel times the strain in the steel, right? And that gives me the stress at that strain. That would be that stress. And the stress in the wood would be this strain, right, that I calculated. Here's the E for the wood and the strain for the wood. And that gives me the stress in the wood. And the stress then does come out below, what was it, 725 I think was the limit for the wood. So they're both safe. This one, the steel is maxed out, is controlling the design, and the wood is, in this case, a little bit below, not fully stressed. So that would be safe. That would be the limit that you could take that to, because the first material failed. Okay, so then we've got to calculate the moments. That's what we were after, were the allowable moments for this thing, capacity in terms of moments. So in the steel, I plug in the value that this is the stress limit that I just calculated. It's at its limit. The transformed moment of inertia. The C is that depth, right, to this depth here, right, was the 3 inches, I guess. and sorry, hit the wrong key. Get back. Okay. Right. And the N value, the modular, is 29. So that gives me a stress of, that gives me a moment capacity of 116. If you did it for the wood, you should get exactly the same number. Now I've got the wood, the stress in the wood that I calculated was a little bit below and this is in KSI, a little bit below its capacity, but okay, that's what it was. And there's the same moment of inertia, and the C value for the wood was a little bit lower. The steel was up on top of it. And I get exactly the same moment. All right, so that kind of checks out, I guess. You get the same value either way. Now, you could do this another way, rather than going through, although it's loads of fun doing the strain diagrams and the strain compatibility and calculating the stresses based on the strains. You don't really have to do that. You could simply put the maximum in for each of these. So this is the max for the steel, and this is the max for the wood, right? The max stress. And I put that stress in KSI in both of them. And then you fill out the rest of it, right? Exactly the same as before. And you get two different values. But the lower one is going to be the one that controls. So this is saying it would fail first here at the steel would control the design and fail first, and this would not happen. That would be overstressed, right? Or it would be beyond, it would overstress the steel. So you can simply work them both and see which one controls. Because that's what you're ultimately trying to figure out is, by all this other stuff we did here, we were just trying to see, does the steel control or does the wood control? That was the question. Which one which one's failing first? And we determined here that the steel failed first and the wood was under design, lower, is safe. So you can do the same thing, simply plug both maximum values in and see which controls, and that would be in this case, the steel. Okay, so one more problem with these. This would be a design procedure to calculate a flitch beam. And what you'd normally be looking for is how much steel to put in there. I mean, that would be, you could do it either way. I mean, you can, like design, it's always a little bit of an iterative process, right? You could go through a cycle and decide, oh, I need more wood and I need more steel, or you need more whatever, or maybe your steel is set and you just want to have enough wood to add to it. But a common scenario would be to take the two pieces of wood as given and find out how much steel you'd have to add to bring it up to strength. So that's the way this is set up. So we're going to look for the amount of steel. You also have to choose the depth of the steel here so that the steel is not overstrained. So if you're designing it, you're able to choose that depth, right? And you're going to assume that the wood is going to be stressed to its limit. But the wood's a little bit weaker material, so if I run the steel up to the same depth as the wood, I'll probably overstress the steel if I bring the wood all the way up to the maximum strain of the wood. So I can't do that, but if I want to maximize the steel to have it also stressed, to have both materials stressed to their full capacity, then I've got to shorten the depth of the steel a little bit. So that becomes a question as to what that depth is. So those two things, the thickness of the plate That's what we're looking for, and the depth of the plate. Okay, we require, all right, find the moment capacity first of the wood, since the wood is given, so we'll see how much the wood carries. Whatever's left over is the capacity for this. That's what we're going to have to require for the steel. Then you check the string compatibility to find how, that would be this procedure here, to find how deep you can go with the steel. And then you calculate the section modulus that's required for the steel plate, and then you can calculate the dimensions of the steel plate from that. Okay, so here's a lovely little example, and this is one that would be kind of a scenario where you might still use these just to strengthen a section of this. So I've got a situation where I have a peak negative moment over these interior supports, right? I've got cantilevers on each end, so the cantilevers are driving this high moment at the interior support. The moment out in the center is actually quite a bit lower. So I could initially determine how much the wood could carry. So I've got I'm a party in the hallway. Okay. Oh, all right. So what do we got? So we got these woods given, and for some reason, again, this problem was set up with full dimensions. So these are actually 2 inches. We'll use these dimensions by 12 inches. And we've got the stress given. This would be would be F prime B is what we would normally call that for the wood as 1500 psi or 1.5 ksi. Okay, so we could find what the moment capacity for this wood is. You know, we'd like to know what the moment capacity is. So first, we can probably just look up the section modulus, but since there are weird dimensions here, I calculated the section modulus. So for one piece, right, BD squared over 6, we get 48. For 2 pieces, we have 96. So we got 2 of them side by side. And then the stress was given capacity as 1.5, so we can quickly calculate the moment capacity for that wood in kip inches or convert it to kip feet. So here's my moment diagram for the whole thing. That's what this dashed line is. The wood can carry up here, right? The wood can do that. And the wood also is going to carry this. So the wood is, the wood is able to do that. So what the wood can't do is this. That's what the steel's got to do. The steel's got to do that. And I've got, you say, okay, how much is that? Well, it's 36 minus 12, right? So that looks like 24 kip feet that the steel has to carry. So that's what what we've got to find, a piece of steel. We just want a plate of steel that's able to carry 24 kip feet. So not too hard a problem, but we have to make sure we don't overstrain it. So the depth here, half of the 12, is 6 inches up to the top of the wood. All right, this is my wood here. And the maximum strain in the wood, given the E modulus I had given for the wood, and the maximum stress, the maximum strain, this would be the maximum, all right? The maximum strain is 0.00075. So that would be that point right there. And now I could say, okay, well, what, given this rather low limit for some reason of the steel, then the maximum strain for the steel is only 0.006. So where does that fall on this line? Well, it falls somewhere, but I could easily find exactly the depth by proportions, right? Because this is a linear relationship, it's just a triangle. So 75 is to the depth of 6, as 60 is to 4.8. So this x here then becomes 4.8 inches, right? That's this distance. Okay, so if I double it, 4.8 and 4.8 is 9.6. The full depth of the steel plate then, this is at the center line, right? The midline, mid-height. The full depth would be 9.6. So I need if I have a steel plate that's exactly 9.6 inches deep, the steel will reach its limit at the same load that the wood reaches its limit. So they'd be balanced in that sense. So that makes sense. We can do that. Now we want to know how thick does it have to be. Okay, so the moment that the steel's carrying is 24 kip feet, the stress is 18 is somehow the maximum stress this has, and we can calculate the section modulus then is m over the stress, so that gives me a section modulus of 16 inches cubed. Right, and I already have the depth, the section modulus for a rectangle, BD squared over 6. I already have this depth here is 9.6 inches, right? So I'm just trying to find that B. So I solved it for B, and it comes out to be a little over an inch, 1.0 something. So realizing that I'm going to actually have to purchase this plate from stock, I guess you can get a plate that's 1 1/8. So I rounded it up to 1 1/8. It would be 1.125. And when I did that, I recalculated the section modulus using 1 1/8 and found that I could get away with 9.5. So I could even reduce it a little bit. And that'll give me a section modulus of 16.9, and I only needed 16. So the steel, I can do it with a steel plate then that's 9.5 by 1 1/8. So we found the steel plate, and that then is compatible with the wood. I mean, they're both pretty close to, the steel plate's a little under stressed maybe, but about at capacity. It's safe. Okay, now the last question would be, how long do you make this steel plate? And that would just be to cover this distance. And that's just simply, you can get that from proportions from the diagrams, probably more easily from the, oh, well, this is linear here, so you could get that. This is, but I probably took it from here. This would be 12. This would be 12 and 24. So 24 divided by 6 would be 4, right? So this is 4 feet there. I'm just calculating that would be have an area of 24, right? So it'd be 6 by 4. So that gives me that distance. And then the other side, or I could have gotten it off of this linear thing. I think that's probably what I did up here, isn't it? I went by that slope, but it comes out the same. And here, it would be a little trickier if this is really parabolic. I guess I could probably write the equation of that and calculate it, but it might be easier to go up to this diagram again. This would be then two proportions, right? And I'd have the area of this one should equal 24, right? And the area of this one is whatever is left from, oh, here we go, 43 minus 24. This area would be 19.2. So I've got a nice little triangle here, and I know the area of it, and I know the relation of this is x, and it has a slope, so I can figure x in terms of that slope. So that's what this is, probably. Here's the area formula. It's the base times the height. So the height is the slope of this line, right, times that length, right, times that's the base. So this is the height and the base. In terms of this, as I'm calling x3, I guess. And oh yeah, like that. And then we can calculate that. So it comes out to be 8. So that would be 8, and this is 12, so this must be 4. So that's 4. So 4 foot and 4 foot, that's where that 8 comes from. So, it's just a matter of finding the dimensions of it. But you can see you'd only need an 8-foot plate over each side, so that saves you whatever this total, what was this, 36, it was 36 feet total, right? And that was the total span of it, and you're only using 16 feet of steel plate, so you saved a good bit of steel plate, which is kind of the point. And that could be either scabbed on the outside, would it honestly be easier, or put in the center, and then you have to put a little spacer somewhere on the center part of it. Okay, well, so that's the design of those, and this is just a couple examples that I found of people that use them. This was a guy up in Minnesota who had a structure that there was a wall here in the original building. There was a wall, and he wanted to take that wall out. And when he took the wall out, he still wanted to keep the ceiling. He didn't want to have a beam protruding in his ceiling, so he wanted to keep the depth of whatever. He had to add this beam in, right, to replace the wall, but he wanted to keep it at the same depth as these joists. And in order to get it strong enough, he flitched in 2 of these steel plates. So the plates were 1/2-inch steel plates, and it was done with pretty small, remember, 2x8. So that's what the original floor depth was. So he was able to take his wall out and have that beam strong enough then. And of course, you can see it attached very nicely with all the, because these joists originally sat on top of that wall, and now they're able to attach to the beam, the wooden part. So that's an example. And there's another one I found. These guys in England, I saw this online, I guess, and I wrote them a letter and asked them because I didn't understand what it was going about. And they write me this big story about, well, they were in this, they had this small house that they were renovating, but it was in a very tight neighborhood. In other words, the distance to the next house was only the width of the driveway. So the houses were like within 15 feet of each other, and they couldn't get a crane in there. They couldn't get even a large beam brought into the house because there just wasn't room. But they wanted to there was a floor here, and they wanted to take I think they took that floor out, or they were building a mezzanine. So I think it was building a mezzanine. That's what it was. So they had these. They had to have a stronger beam, and there wasn't room. They couldn't physically get a real big beam into the building, and they had to do it. They couldn't do it with a crane. It had to be light enough that they could carry it. So they couldn't just have a steel member because they couldn't carry it, and they couldn't have a big member. Also, I guess because they couldn't carry it. So what they did is they built the flitched beam in place. They brought in the dimension lumber and the steel plates. They had to cut a hole somewhere. Oh, they cut a hole in the roof and fished it through the roof, and then built this thing in place and bolted it all together and had their beam. So I guess, the moral of that is, yeah, okay, that's one advantage of them. You can construct them in place, right? You can have the steel brought up separately and the wood and then bolted together, and people could do it by hand without heavy equipment. Okay, these are some examples. This, I think, is Simpson Strong Tie makes these special attachments and uses them with lightweight W sections to get members that are used in wood construction. So that's their little variation on it. And then this is just a little bit about stuff I found on concrete. These, if you look real closely, they're at different depths. This is going, it's hard to see in this photograph, but it's castellated like that. And I think the idea is it's keyed into the wood plate, and they're making a plate out of, I don't know, 2x6s and 2x8s maybe, and then they cast over it, and they've got these special these ties. They look kind of like, the Nelson studs that you use on steel construction, but they're screwed into the wood actually, so, or with pretty substantial screws here, and then those tie to the concrete. You would, interesting here in the photograph, they've also got that foiling, the waterproofing, a moisture barrier between the wood and the concrete, which to me would make a lot of sense. Otherwise, you run the risk of the moisture in the concrete over time. If moisture gets into the concrete, moisture tends to get absorbed by concrete, and then it would be on the wood. That might not be so good for the wood. Although, yeah, there is a little black layer there too. They got it here too. You just barely see it. Anyway, so that's one way to do it. What they do this more often with now are, instead of using something like this, they'll use CLT, and they'll do a CLT base and put sometimes even just a thin concrete as a wear surface on top of it, or it can actually add to the strength of it, of the CLT panel. And these are other composite where you have like maybe a glulam beam that's physically attached with a connector here that would be like a Nelson stud but driven into the wood, and then you get that composite action with those. And they make these special connectors like this. This is the one we saw on that other example. And then there was a paper that did a whole study on the stiffness of these different connectors, which connector actually provided the most, the stiffest connection. And it looked like glued one, although I'm not exactly sure how they glued what they glued. Something. Okay, well, that gives you a little bit of an idea what flitched beams are like. Overview with those.